Today I'm going to be presenting a demonstration for measurement of temperature sensor intensity and distance laboratory for experiment 1. So it is say here that for the first point, connect the left pin of the MP36 to a power source of 5 volt and the right pin to ground as shown in figure 1. Then the middle pin will have an analog voltage. Then we have to record the value of voltage change versus temperature. Okay, so here I have done it on Tinkercad as what have been asked from the lab. So here we could see that around we can control the temperature and the multimeter will show the voltage of the sensor. This is for the number 1 point. For number 2, I need to design an application circuit, a signal conditioning circuit to produce a maximum output voltage of approximately 15 volt to 18 volt for maximum temperature change. Okay, so here I'm going to show for the second point. Okay, for this is the signal conditioning circuit. As we could see, I need to increase it up to 20 volt as mentioned that the maximum output voltage of approximately 15 volt to 18 volt. Okay, so from there we could see the output voltage. This is the minimum and then the maximum is around 19.2. So that's for the number 2. And then I have collected data as we could see here. This is the result for the point 1 where no signaling circuit condition. I pick the temperature from 25 to 95 and then this amount of the output voltage. Here is the graph, and then for the second point, part 2, here is the record for the output voltage and then the amplification voltage. I use the same temperature as the part 1. This is the temperature versus output voltage and then the temperature versus amplification voltage. That's all from me. Thank you.
Here come to experiment 2, intensity measurement using photoresistor. Okay, first, connect the photoresistor to an ohmmeter. Okay, here, the photoresistor is connected to an ohmmeter. We start simulation. Okay, so from the dimmer to the lighter, so which is from 0 scale to 12. Okay. I just based on these scales of intensity here. Okay. So we get the value and record it in a table here. Question 2. By using a voltage divider circuit, design a signal conditioning circuit to produce a suitable output voltage from your signal voltage divider circuit. Okay, so here is the voltage divider circuit. Okay, this is a 10 kilo ohm resistor. Okay, we start simulation, and then we just vary this light intensity based on the scales from 0 to 12, and we will get the voltage output. Okay, we can see that if the brightness of the light intensity of the photoresistor increase, the voltage output decrease. You see. Okay, so after we got all this value, we record it in the table here from 0 to 12, and then this is the graph of voltage versus intensity level using voltage divider. Okay, you can see the graph, the line is decreasing as the intensity of light increase. Question 3. Repeat part 2 by designing a Wheatstone bridge circuit. So here is the Wheatstone bridge circuit, this one. Wheatstone bridge circuit actually is just two voltage divider circuit, and we parallel it together, and then we form a Wheatstone bridge circuit. Okay, so we have used 10 kilo ohm resistor in our Wheatstone bridge circuit, one photoresistor, and a potentiometer with 2 kilo ohms. Okay, so we start simulation. First, we put it the light intensity to max first, and then we vary the potentiometer to get the output voltage at approximately 0 value. Okay, so put it at 28.3 millivolt, approximately 0. Okay, this is because we want to make the circuit balance. Okay, so this Wheatstone bridge circuit, the voltage value, the output voltage value would not depend on the input voltage, but it depends on the ratio meter of the resistor. Okay, after we got an approximately 0 voltage between point C and point D, then only we vary the light intensity of the photoresistor and check for the output voltage. Okay, as we can see, from dimmer to maximum light intensity, the voltage output is decreasing. So the results are recorded here in this table. Okay, and this is the graph.
Okay, for the experiment 3, we want to measure the distance measurement using ultrasonic sensor HSSR04. This is a figure for the object, for the sensor. Okay, firstly we connect this this sensor with VCC voltage supply 5 volt, and we connect to the oscilloscope with the square wave oscilloscope. Okay, for the experiment, we want to find the relationship between the pulse width for the oscilloscope with the distance between distance between the sensor with the object. Okay, so we connect. Okay, for the according to the instruction, this is a 5 volt for the supply. This is a oscilloscope, and this is a monitor for the oscilloscope, which present the wave. Okay, let's be fine. Okay, okay. When we put the object nearest to the sensor, we can present that the pulse wave 20 for the 10 box must divide by 10, so we can get for one box is a 2 millisecond. So for the nearest object to the sensor, which is 34.8 centimeter, is a present 2 millisecond for pulse wave. Okay, when we try to put the object, for this is present the increase the pulse wave. This is a 4 pulse wave. This is a 6 pulse wave, 6 millisecond pulse wave. This is a 8 millisecond for pulse wave, and this is a 10 millisecond for pulse wave. So we can conclude it. The highest distance for the highest distance from object to the sensor, so the highest value of pulse wave. This is a distance for the sensor and object. Okay, that's all for experiment C. Thank you.
Okay, next we're going to continue with my experiment 4.2. I've done my circuit and constructed as this one, and I'm going to start the simulation. First, I put 25 volt at the power supply, since it is the optimum voltage, and then I'm going to set the temperature to 0. When 0, we're going to achieve 5.9 volt with 10,184 RPM. Next, we're going to increase it by 10. We're going to achieve 5.99 volt with 11,981. Next, we're going to increase it again by 10. We're going to get 14,177 RPM with 7.09 volt. Again, increase the temperature by 10 to 30 degrees Celsius. We're going to achieve 7.99 volt with 15,974. Next, we're going to increase by another 10 degrees Celsius to 40 degrees Celsius. We're going to achieve 18,170 RPM with 9.09 volt. Next, we're going to increase again by 10 to 50. Oops. we're going to achieve 9.9 volt with 19,967 RPM. Next, we're going to increase again by 10. We're going to achieve 11.1 volt to 22,162 RPM. Next, we're going to increase by 10. We're going to achieve 11.3 volt with 22,648 RPM. Next, we're going to increase again by 10. And unfortunately, the DC motor still have the same 22,648 RPM, and the multimeter also shows the result of 11.3 volt. How about we increase again by 10 to 90 degrees Celsius, and the result is still shows the same. So how about we decrease it to 6. So it shows that at certain point the the result will show constant result. So we have to find the constant point. Over 68 still shows the constant point. 67 still shows the constant point. 66 still shows the constant point. 65 still the same. 64 still the same. 63 still the same, and 62 and 63 62. The RPM shows different reading, so we can conclude that the reading will maintain the same when it starts from 63 degrees Celsius. Okay, since we've achieved that 63 degrees Celsius will shows the same constant result, therefore I've already record my result is in the following table. Here it shows when the temperature reach 63 degrees Celsius, the speed will be constant at 22,648, whereas the voltage will be constant at 11.3 volt. Therefore, we can achieve this graph when we change our voltage to millivolt. That's all from me. Thank you.